I should apologize first for the clickbait title, but I guess it worked. Thank you for coming. Well, it actually led to some very interesting conversations I had before the talk. People kept asking me, so what will you talk about? And I said, I'm going to talk about the flat Earth theory. You're kidding, right? No, I'm not kidding. I'm serious. I'm totally serious. So let's start with a show of hands. How many of you believe that the Earth is spherical? Almost everybody, huh? Tough crowd. So let me reformulate this question. How many of you believe that the Earth is a perfect sphere? Nobody. Okay, so the Earth is not spherical, really, right? So there are these two theories, competing theories, right? One is that the Earth is spherical, and the other is that the Earth is flat. And as we can see, it's not really spherical. We freely admit that, I mean, if it were a perfect sphere, we would be constantly slipping on it, right? So first of all, in the old times, people really believed that the Earth was flat, and it was. Why did they believe that? It's a natural theory. It's what we use in everyday life. We don't really think about Earth being spherical in like day to day. We pretty much treat it as a flat thing, and in fact, with new technology, we use this model of flat Earth all the time when we are trying to find something. We're trying to find the gas station or the ATM. We use this device, right? And we are not carrying with us a spherical object, right, to find places. And when we are looking for something, the screen of the phone is not bulging, right, to take into account the curvature of the Earth. So this flat Earth theory, to a good approximation, is very useful in everyday life, right? And this is true about every physical theory so far. It has its limits of applicability, right? Physicists think about eventually coming up with this one general theory of everything that will be applicable to every single situation. But we haven't found one yet. So what I want to talk about is, at least to start you thinking about this, is the modern version of a flat Earth theory. Okay, because most flat earthers, they don't really study the theory very deeply. They just believe what they see. But imagine a world in which it's sort of forbidden to talk about round Earth. Maybe for religious reasons, the government doesn't want people to do this. So the scientists there, and they have good science, right? The scientists there start with this flat Earth theory, and in the beginning, when it's applied to small areas of the world, it works perfectly well. But then they start thinking about, they start traveling, right? And here's the map of the flat Earth, right? And they find out that the further they go from the center of this disk, right, weird things start happening. Because by looking at this, you would see that these circles, the concentric circles, they should be growing in, as the diameter grows, they should grow in circumference. But what they see is that they are not actually growing as fast as they are supposed to. And actually, after reaching what we call the equator, they start shrinking. So they have their Einstein, and this guy comes up with this theory that, that what happens is that when you take a measuring rod to measure distances, or a laser or whatever, and you go further from the center, the measuring rod actually starts expanding in the direction perpendicular to the latitudes, right? When you turn it back, it shrinks again, right? And they develop this theory, and they develop, and eventually they find out that when you get to this outer circle, you get into some kind of singularity, right? The distances just grow to zero, and the measuring rods grow to infinity, right? And we might think this is like totally crazy theory, but we have examples of a theory or several theories that kind of work like this. Like if you know anything about special relativity, it's also a theory that we don't use in everyday life. But when we think about speeds that are close to the speed of light, then suddenly the measurements change. Like the measuring rods shrink in the direction of light. But you turn them perpendicular, they re-expand. So it's a very similar situation. And in general relativity, when you get closer to the event horizon of a black hole, also weird things happen. Not only to distances, but even to time. Right? So in fact, these people from the flat Earth society, they would be better prepared to talk about general relativity because they already have the math to do that. Okay? And I know that this theory with the expanding rods actually is a perfectly good theory. Because I know that we can go between different coordinate systems. It's just a matter of changing the coordinate system, right? We measure distances instead in angles around, starting from the North Pole, and we get a different coordinate system. In that different coordinate system, all this stuff that I described actually is true, right? So it's not like one theory is correct and the other is incorrect. So you might ask the question, why do we think that the Earth is spherical rather than flat? Why don't we use this weird theory with expanding measuring rods and so on? Well, the reason is practical, right? And there is even something called the Occam razor. Occam's razor says that, the theory that's simpler wins. But is this the law of nature? I don't think it's a law of nature, right? This is something that cannot even be tested because it talks about theories, not about nature. So we like these theories that are simpler, but that's our preference. The nature does not abhor complexity. In fact, nature is extremely complex. But our brains avoid complexity. We prefer simpler solutions. Okay? So let me talk about how science developed. Okay? There is the scientific method that we use that's based on Occam's razor. So the person who first actually came up with this layered cake philosophy, that I call it layered cake, he didn't call it this, it was Galileo. Galileo thought that nature, the universe, has 3 layers. Okay? One layer is this nature. This is what we observe, that we measure, we do experiments with, right? But there is, behind it is a second layer of physics, the laws of physics. They exist. We just have to figure them out. So when we are studying nature, we actually look at this indirectly at the laws of physics, and we figure them out. We don't see them directly, but we figure them out. And then there is a third layer behind physics, and that's mathematics, which is the language of physics. This is where we get our models that we use in physics, right? So we have these 3 layers, and the question is, do these 2 other layers exist in some way, or is it in our imagination? Does the universe actually contain these layers or not? Right? When we do physics, we actually test our ideas against experiment, right? When we do mathematics, do we discover mathematics? And if you ask a mathematician, most mathematicians believe that mathematics is discovered, that this is actually something that exists in some way that's different from nature, right? It's called the Platonic ideals. So let's talk about these Platonic ideals, because what happened is that physics or our knowledge of nature went through several stages in which we came up with simplified models of reality, and they were sort of very elegant and nice. Like if nature really abhorred complexity, these models should have worked, but they didn't. We had theories. Well, so here's an example, right? This is the celestial spheres. This is how people imagined how the universe was organized. And spheres are Platonic ideals, right? So they always wanted to fit the Platonic ideals into our world. Now, right now we know that actually there are no spheres, and that actually planets revolve around the sun, around some very complex orbits, right? But we always look for this elegant theory of the universe, and we think mathematics is very elegant, and physics should be elegant too. And we try to formulate laws of physics in terms of very simple mathematical equations. And somebody said it's like a matter of beauty and elegance. But we have these examples. Celestial spheres, for instance, they are very elegant, but they didn't work, right? There was this theory that all matter consists of 4 elements: earth, water, air, and fire. That didn't work, right? Ether, right? There was this idea that light, electromagnetic waves, since these are waves, they have to have some kind of substrate in which they work. So there was this elegant theory of ether, also wrong, right? But so maybe mathematics is elegant, and actually there was like a huge project at the end of the 19th century, beginning of 20th century, to formalize all of mathematics. Like there was this beautiful idea that you can have axioms, and from axioms you can prove all the theorems, and everything works nice. And then this guy came, Gödel, and he said, in every theory that's not a trivial theory, there is a theorem that cannot be proven to be right, correct, true, or false, right? So even in mathematics, we see this like, lack of elegance, something that we think math should be like, and it's not. So, but physicists, I used to be a physicist, so I'm kind of talking from this perspective. Physicists always were very practical people, right? So the way they dealt with complexity was always to create a simple model and then find out little corrections to this model. This is called perturbation theory. The first example of this is when people were calculating the positions of planets. So this is a table, I don't know, from 18th century or so, you know, where they're calculating positions of planets. And they were doing this by assuming that essentially a planet, so let's talk about celestial mechanics. Essentially, the planets go around the sun. First they thought in circles, then ellipses, right? And this is a solution to a simple problem of, it's a problem of a body moving in a central field, gravitational field, right? That's something we know how to solve. We can solve this, we have solutions, right? Two-body problem, also solvable, right? So we take the planet, we take the sun, and they move around, right? And we can solve this. Three-body problem cannot be solved, okay? So the way to calculate the movements of planets, because there are many planets, right? There's like, if you want to calculate the movement of the Earth around the sun, we have to take into account that there is Jupiter also that interacts, right? And that just throws it off. So we have this perturbation theory. We take the original solution and we just add little corrections to it. Little tiny corrections, and we calculate these corrections, right? So this ephemerate tables was calculated using this method of adding up little corrections to the original simplified solution, right? So this idea that we can simplify some problem and then calculate little corrections to it, that was very important. Unfortunately, this does not work. This does not work because these corrections get bigger with time. So like if you calculate this up to 100 years or so, well, that's still fine. 1,000 years, everything blows up. What we get is chaos. Okay? So, I mean, you've heard of chaos theory, right? Like the butterfly effect and so on. So the universe is filled with these butterfly effects. We can only calculate things up to a certain degree, and then everything blows up. So maybe in the microcosm, though, maybe things are more organized, because this is very disorganized and chaotic. So let me give you this picture. This is the currently best theory of elementary particles. See, there are quarks, there are gluons, photon, there's the Higgs boson, okay? What you notice is that there is, it's a table. It looks like a periodic table of elementary particles, right? We've seen tables like these in chemistry a long time ago, before people knew that there was atomic theory of elements, right? And when you see this kind of periodicity, you start thinking, okay, maybe these are not really elementary, right? So this is kind of messy, but we have no idea why these things are periodic. So I'm showing you, you know, like we are at this point in science where we got very, very far, but we hit a wall. And this is something from the 60s of the last century, okay? And we haven't made progress yet. This is a picture of some particles, elementary particles from a bubble chamber. Now what you see is that they really look like particles. When I say particles, I mean particles, right? They look like particles. Are particles like little rocks? You know, do they behave like little rocks? I mean, they sort of look like they have trajectories. Like if you throw a rock, it has a trajectory, right? So maybe particles are like little rocks. Well, they are not, okay? Because in some experiments they behave like waves, okay? But so maybe they are waves. Well, no, they are not really waves because we can count them using Geiger counters. Like so are they are they particles? Are they waves? And why do we insist on them being particles and waves? Why is, like, physicists now think they are neither particles nor waves, right? Sometimes they look like this, sometimes they look like this. Which means we don't really understand them. And physicists, you know, there are some physicists who say they understand quantum mechanics, but Richard Feynman was like the greatest physicist. And he said anybody who says that they understand quantum mechanics is lying. And it's really true, I think, okay? But why can't we understand this elementary particle? We try to understand it as a particle, we try to understand it as a wave, but we cannot understand its real nature. Why do we want things to behave like particles? Because particles are decomposable. It means like if you have a system of two particles, you can decompose it. You can look at one particle, calculate its movement, then you can look at another particle, calculate its movement, and the two-particle system is just a sum of these two. Okay? If there is interaction between them, you can add the interaction, maybe third particle being exchanged between them, and so on. But this is something that is nicely decomposable. Complex system becomes a sum of simple systems. Same thing with waves. Waves can be decomposed. Like we have a Fourier transform, right, that can decompose a complex wave into its individual components. So what we are hitting here is the breakdown of decomposability or composability, okay? So this is very important. It's like everything that we've learned so far was in terms of things that were decomposable into simpler things. And now we hit this problem with a two-particle system when you have two elementary particles. This is not something that is decomposable. If you try to separate them, right, you can have them even far away from each other. What you get is this spooky action at a distance, the quantum entanglement, which means that a two-particle system is not separable into two simpler problems. It's a problem that cannot be separated into simpler problems. And these kind of non-composable phenomena are totally alien to our way of thinking. And this is something I've been thinking about a lot. Why is it? Okay? But physicists, you know, practical people, they actually can do some calculations. So for instance, going back to perturbation theory, right? So we've seen that it didn't kind of work with the planets. I mean, it worked to some extent, but then it broke down. In particle physics, we also have a similar perturbation theory way of calculating things. These are called Feynman diagrams. Feynman diagrams, this is a Feynman diagram that describes to the first approximation. So this is like thinking of planets going in circular orbits. That's like first approximation. Here the first approximation is two electrons exchanging a photon. This diagram, when you translate it into mathematics, actually gives you the repulsive force between two particles. It's like the Coulomb law, right? So this gives us classical electromagnetism. Now there are some quantum effects. We don't really see them in everyday life because they are small quantum corrections to the big picture, right? So people try to calculate these corrections, and what they find is not only they are not smaller than the original solution, they are actually infinite. So the first correction to this diagram involves the exchange of two photons instead of one photon, and it blows up. It's infinite. So we have found a way of kind of cheating mathematically. It's called the renormalization theory, to get rid of these infinities or hide them under the carpet, right? And it sort of works, right? But it doesn't really give us a better understanding. It just shows us that the way we are decomposing a complex problem into simpler problem plus perturbation really kind of breaks down. And the whole standard model is kind of based on the same idea. It's a more complex interaction, but still, it's renormalizable. And there was like a big deal when people actually found out that it was renormalizable. And we can calculate a lot of stuff using perturbation theory in the standard model as well. But then it breaks also. It breaks, you know, it's like quarks, when they are close together, they behave more like free particles, so we can use perturbation theory, but when we try to separate them, then perturbation theory breaks down. So we are just like only looking at a tiny part of nature that we can deal with, and the rest is still not accessible to us, okay? But the biggest problem with the standard model is that it doesn't really provide us with understanding. I mean, you've seen, the standard model does not explain why there are 3 generations of elementary particles. It doesn't explain why the masses are different, what are the interaction constants, and so on. Why the Higgs boson has this mass and not the other. And then finally, there's this big problem with gravity. Gravity is not renormalizable. Okay, so this whole trick with hiding infinities under the carpet does not work for gravity. Gravity is like the example of this theory that simply cannot be decomposed into quanta. So physicists have been struggling with this and you know, coming up with things like strings, like membranes, there's M theory, and so on. But these theories really are just expanding mathematics. There is no connection between them and the experiment. So, physics is a mess. Okay? So there are these several things that, like, why do we have 3 generations of particles? You know, why gravity resists quantization? We have no idea. You know, strings, they don't simplify things. Even people who work in string theory, you know, will say, okay, so one complexity is exchanged for another complexity. Maybe string theories, there are fewer of these string theories, but they have infinitely many possible vacuums. And like our universe picked one of the vacuums, and we don't know why. So like, you know, you exchange complexity in one place, it pops up in another place. And this is the truth. There was really no progress since really end of 60s, beginning of the 70s. There was no proof. And you can sometimes hear physicists saying that, you know, it's like they look at the experiments in CERN and saying, maybe they will find something that does not fit the theory, which by which they mean the standard model. And they don't see anything. They wanted to see supersymmetry. They wanted to see strings. Nothing shows up. So it's like totally. I mean, usually you don't hear physicists saying this because they have to write grants, you know, and they have to get money from the governments to. So if they say what the real situation is in physics, right? They wouldn't get the money. Yeah, so this is the situation. There was the standard model in the end of 60s, beginning of 70s. It's a kitchen sink of particles. We figured out the Higgs mechanism and the renormalization of broken gauge symmetries. We figured that out, worked nicely. So, but maybe this is a temporary setback, right? So this is the idea that physicists always think, it's like, okay, so we had this 50 years of nothing happening, but any time now will have an explanation, right? And it's been going on already for 50 years. So maybe, I don't know, maybe there is time to just maybe sit back and rethink things. Because it's all based on our assumption that the universe is knowable, right? That we can actually figure out the universe, right? And this is actually a strange kind of belief, because there is this major impedance mismatch between the complexity of the universe. Like, the universe is huge and extremely complex. And the only tool, well, maybe we have more tools, but like the main tool at our disposal is this thing here, right? The monkey brain. I mean, we have evolved from monkeys not that long ago, from apes, okay, but I like to call it monkey brain, right? This is, compared to the complexity of the universe, this is such a simple tool, right? It's slow. It has, what, a few billion neurons? I mean, what is that? It's nothing compared to the complexity of the universe. And now we are saying that somehow we can create a model of the universe in this monkey brain, right? And we can play with it. And we can predict stuff on huge scales, right? And why do we believe that? Well, because we've been very successful so far, right? We have been successful. But we have been successful because nature had to solve this problem to some extent, right? Because in order to survive, animals or have to create in their mind some kind of model of like, what, this is a predator, this is food, run away from predator. So there is this kind of model of the universe, or at least the surrounding universe in our brains and in the brains of even simpler animals, right? So nature came up with this ingenious hack. Namely, during evolution, we learn how to decompose complex things into simpler things, and then combine the solutions, compose them to form the bigger solution. So this procedure of decomposing and then recomposing solutions, that's an amazingly powerful tool that we've been using so far. We are creating these models of the universe that are simplified models, right? But they are composable. So what I've been talking about all this time is like taking complexity, finding a simple model, and then maybe making corrections to it, or separating things into, this is the sun, this is the earth, this is one particle, this is another particle, this is one wave, another wave. Let's solve one problem at a time, combine them. And when we are developing science, we also do it by composing things, right? Like, sometimes there's one scientist who comes up with a great theory, but in most cases, like a huge group of scientists, they are working on solving problems. They are, exchanging emails and publishing papers and reading papers and so on, which means that the problems that they are solving are decomposable, right? Because they can decompose them so that you take this part of the problem, I take this part of the problem, you take this part, and then we combine our efforts and we get a new theory or new publishable result, right? And we do this by either combining simplified models or making corrections to a simplified solution. Okay, so this is so far, this is physics, right? But what is mathematics then? Okay, well, mathematics is all about composability. This is like the science of composability. That's what mathematics is. Have you heard of this Curry-Howard-Lambek isomorphism? This is like was the first time when actually things kind of clicked to me, for me, that there are these three different theories that were developed separately: constructive logic, type lambda calculus, and category theory, and the isomorphism says that these are actually identical. It's not like they are similar. These are identical theories. They might use different names for things. Why are these three completely separate theories have the same structure? Why do they have the same structure? Because all three of them are about composability. Okay? Like in logic, you compose predicates by saying this and this or this follows from this. Identically, in lambda calculus, you know, when you combine data structures, you can have product types, right? You can have sum types, and you can have function types. So exactly in one-to-one correspondence with the three things in logic. And in Cartesian closed categories, we have categorical product, we have co-product, and we have an exponential. They serve exactly the same purpose. And what's common about them is they are used to combine things, to compose things from simpler to more complex. So, which is it? Is composability the fundamental property of the universe that we have discovered? Or is it the way we figured out how to deal with complexity? That's a big question, because if this is a fundamental property of the universe, then we are really, really lucky, right? It just so happens that the universe was like created for the purpose of monkey brains to understand it, right? Why should it be? I don't know. So when we are discovering mathematics, so mathematicians like to think that they are discovering mathematics, these Platonic ideals, right? And I would say, well, maybe we are just discovering the ways our brains work. Because if mathematics is all about composition, you know, then composition is something that our brains came up with in order to deal with complexity. And it's been amazingly successful, right? So far. And still, like, we are still discovering new things. So a lot of people think, okay, since it's been so successful, it will go on forever like this. But there are different explanations. One explanation is that it's called the Streetlight Effect, right? It's like, there is this joke that a drunkard is like going around a street light. It's like, imagine this is a street light, right? Searching for something. And the policeman comes and says, what are you looking for? Well, I lost my keys. Okay, and the policeman tries to help him. Finally, he says, are you sure you lost them here under the street light? He says, no, I lost them in the park. So why are you looking for here? Why are you looking here? Well, because there's the light here, right? So maybe it just happens that the composability is this light. Like, we only see things that are decomposable and just ignore things that cannot be decomposed. And like right now in physics, we are kind of hitting this wall because we are starting to look outside of the street light. And we've been also successful because we were coming up with better and better ways of decomposing things. So all these developments in mathematics actually provided us, because there is not one way of decomposing things. There are many different ways of decomposing and recomposing things. And mathematics is all about these new ways of composing and decomposing things. So if we are moving mathematics forward, more and more things become accessible to us because we are better at decomposing. But it's still perfectly possible that there is the universe outside of the street light, right? That's not decomposable. But maybe computers can help us. Okay? This is an illustration of this four-color theorem. The four-color theorem is that any planar graph can be colored using only 4 colors without any two touching each other, right? So this is a very interesting example because it was solved using computers. People were trying to prove this theorem and failed miserably. There are many theorems like these that people failed, but this one was interesting because there was eventually people wrote a computer program that proved it. The problem with this it was a decomposable thing, right? But the decomposition just produced so many special cases that it was impossible for a single person or even a group of people to go over all of them. So they wrote a program. Initially, it was like more than 1,000 different cases. They simplified it nowadays to 633 cases. So it's like proving 633 separate theorems. Okay? So that's a lot of work. So computers can help us doing mathematics, but this is only a quantitative improvement. Like, okay, so this theorem is still decomposable, it's just that it decomposes into too many moving parts, right? So there is computers can help us doing the calculations, but the decomposition has to be there, right? Because computer programs themselves are composable. Right? I mean, we are programs. We know exactly that every program is composed from little parts, smaller and smaller, and so on. Right? So maybe these guys can help us. Neural networks, right? The AI. We actually, as humans, have two ways of dealing with nature, right? One is by logical thinking, by analyzing, and the other is just like an immediate recognition. Like when we recognize faces, right? When we recognize faces, we know immediately we don't have to decompose it into eyes, nose, and mouth. We just say, oh, this is my friend John. Oh, I recognize him. So neural networks kind of model this way of perceiving reality that is more immediate, right? And so maybe neural networks could help us like study complex phenomena, right? And in some cases, the problem is that we cannot really ask the neural network, like, how did you come up with this solution, right? The neural network sort of knows it. It was trained to recognize certain things, and it just recognizes them, right? There is some level of understanding that we can like extract or reverse engineer from a neural network, like maybe the first layer of the neural network, the convolutional layer or so, creates a few abstractions, right? And this is probably how we humans came up with these abstract ways of thinking that we actually had to compress all the data that is coming to us and come up with a few abstractions, right? So maybe neural networks also can produce these compressions and abstractions, right? But the problem is that maybe they can come up with some abstractions, but these abstractions could be extremely complex, right? Like what are complex abstractions? This is a arbitrarily complex abstraction. Monad is a monoid in the category of endofunctors. How many people understand this? Oh, there's one. Okay. Okay, so this is an abstract thing, right? But in order to understand this abstract thing from category theory, you have to study like for years, right? So what if the neural network comes up with some abstraction and says, okay, something like this, monad is a monoid, okay? But what's a monad? What's a monoid? What's a, it's like, in order to explain it to a human, it would take 100 years, right? So maybe AIs just won't be able to explain stuff to us. Maybe they will understand certain things, but they won't be able to tell us how. And we won't be able to reverse engineer that, right? And at the bottom, neural networks are also decomposable, right? They are like better brains, but they are still brains. They are not monkey brains. Maybe we can make them more powerful. And if we make them more powerful, then are we going to understand more things? So I want to leave you with this question, what if this decomposition program fails? What if we hit this barrier and we say, so far we've been able to understand nature to this point, but beyond that point, things are just not decomposable. So I have a pessimistic scenario here that the universe maybe is decomposable, but it just has too many components, right? So the neural network of sufficient complexity can actually find the theory of everything, right? Sort of find the physics, the laws of physics that govern the universe and build the mathematics to do this because things are decomposable in the universe, right? But it won't be able to explain it to us. So this is my fear. I'm not really afraid that the AIs will kill us or some, the fear is that we will go to the AI and ask, so how do you combine quantum theory with gravity? Do you know? And then the AI will say, yeah, okay, yeah, I know. There is a theory for that. So how do you do this? Well, I'm sorry, I can't explain it to you because you have a monkey brain, okay? There is just an impedance mismatch. And the optimistic scenario is not that much better. Well, so the good news is we don't live in a computer simulation. What does this mean? It means that if the universe is not decomposable, right, then we simply cannot, there are no simple laws of physics that you could program into a computer and say, once you start running it, you are simulating the universe. So in a sense, the complexity of the program to simulate the universe is equal to the complexity of the universe. So if somebody builds a computer to simulate the universe, they are actually building the universe. So we cannot really call it a simulation. So the universe has this irreducible complexity. And unfortunately, that also means that we won't be able to understand the universe. So I'm sorry. That's all I have to say. Thank you.